Hello, friend. I'm glad you've drifted to this quiet edge of the night. Let the day fall away like a gentle tide, and let the room around you settle into something soft and unhurried. This is Fall Asleep to Astronomy, a small lantern-lit space for restless minds and tired hearts, where the universe speaks in a whisper and nothing needs to be figured out before sleep. Tonight, we're going to wander into a quieter corner of cosmology, where emptiness has its own kind of story. Some astronomers think we might be living inside a vast, underfilled bubble of the universe, a cosmic hollow so wide and faint that it could be bending our measurements and nudging the universe to look stranger than it truly is. Not a dramatic explosion, not a bright flare, just a silence big enough to matter. We'll hold that idea gently, turning it like a dim globe in our hands, never rushing, never forcing meaning. And if these soft night journeys bring you ease, a gentle like and a quiet subscribe help other sleepy travelers find their way here too, only if it feels right. For now, let the world dim around you. I'll keep the pace slow and warm as we step into the mystery of the cosmic void together. Imagine, just for a moment, that we are not floating in some average patch of the universe at all, but drifting through a kind of cosmic hollow, not a sharp-edged hole or a dramatic tear, just a huge, quiet, underfilled region in the vast web of galaxies. From far enough away, it would look like a pale bubble in the sponge-like structure of the cosmos, with our Milky Way and its neighbors hanging inside like dust in a sunbeam. That is more or less what three astronomers, Brian Keenan, Amy Barger, and Len Cowie, suggested when they pieced together their data. When they looked at how bright certain supernovae appeared, how their light was stretched, and how galaxies clumped together over billions of light years, something subtle but insistent showed up. Close to us, space seemed a little too quiet. There were fewer galaxies, less clustering than the average universe would predict. Farther out, the web thickened, as if we were sitting in the thinned-out center of a very large bubble in the cosmic foam. In their calculations, the matter around us, all the galaxies, gas, and dark matter woven into this region, added up to about 20% less than the cosmic norm. Not a tiny nudge, not a bit of local unevenness, but a whole patch of space, perhaps 2 billion light-years across, that is measurably underdense. That gently underfilled bubble is what people now call the KBC void, after the initials of the team who described it. To see why that matters, it helps to remember the quiet assumption that sits underneath almost all of modern cosmology. When scientists use Einstein's equations or talk about the average expansion of the universe, they lean on something called the cosmological principle, the idea that on large enough scales, the universe looks essentially the same, no matter where you stand or which way you look. Not identical in every detail, but statistically even, smooth enough that no place is truly special, if that is even slightly untrue where we live. If our neighborhood is significantly emptier than average, then all of our careful measurements are being made from a slightly odd vantage point. Less matter means weaker gravity in our surroundings. Weaker gravity offers less resistance to the stretching of space, and space that stretches more easily will make it look, to an observer inside that region, as though the whole universe is expanding a bit faster than it really is. That quiet twist slides us directly into one of the biggest open puzzles in modern physics: the mismatch in how fast the universe seems to be growing. When astronomers read the oldest light in the cosmos, the afterglow of the Big Bang, the cosmic microwave background, they fit it with their best models and find one value for the expansion rate. It comes out to something like 67 kilometers per second for every megaparsec of distance, a steady, measured pull. When others look closer to home, Using stars and supernovae in galaxies within a few 100 million light-years, they find a larger number, closer to 73. On paper, it is only a difference of a few kilometers per second, per megaparsec. In practice, it opens a crack big enough to change the age we assign to the universe by hundreds of millions of years. That stubborn discrepancy is what people call the Hubble tension. For a long time, the debate around that tension has been noisy and creative. Maybe there are new particles we have not yet seen, or a strange phase of dark energy early on, or some subtle flaw in how we calibrate the brightness of our standard candles. But in the background, there is also this softer suggestion, almost like a whisper. Perhaps the space around us simply isn't typical. Perhaps we are doing our measurements from inside a slowly expanding hollow. Picture the universe again as a sponge, or a piece of bread with bubbles baked through it. The galaxies are not scattered evenly like dust. They gather in filaments and clusters, long strands and knots of matter. And in between those strands sit the voids, the bubbles. Most of the volume of the universe belongs to these empty regions, not to the bright chains of galaxies. We live in one of those bubbles, surrounded on distant sides by great walls of matter. Giant clusters like Coma, Perseus, Pisces, Shapley, and many others, knitting the edges of our underdense patch. Inside a void like that, the gravitational pull is softer, like the calm after a storm. Light from distant galaxies must pass through this gentle hollow on its way to us. As it travels, its energy is nudged, not just by the gravity of what is there, but also by the relative lack of what is not. Tiny changes in the energy of that light show up as slightly cooler or warmer blotches in the cosmic microwave background. Satellites like WMAP and Planck have seen such cool spots lining up with known voids in the galaxy maps, as if the emptiness has left its fingerprints on the oldest light in the sky. Newer missions, like the European Space Agency's Euclid, have been sent out with the specific task of mapping these structures in exquisite detail. Not just the bright filaments, but also the great gaps between them. Simulations run on supercomputers suggest that voids are not accidents. They trace the unseen skeleton of dark matter itself, growing and stretching as the universe expands. And inside them, where gravity relaxes, the mysterious push of dark energy becomes more obvious. The emptier the region, the more the expansion seems to run free. In 2019, for instance, Seshadri Nadathar and others modeled how large, underdense regions affect what an observer like us would measure. Their results, and similar work by other teams, all pointed in the same direction. Someone living inside a sizable void will naturally infer a higher expansion rate than someone in a denser environment. The more underfilled the region, the stronger the effect. For a supervoid the size of the proposed KBC bubble, the bias could be big enough to account for a significant fraction of the Hubble tension. If that is the case, then the age of the universe, the often quoted 13.8 billion years, might be just a little off, nudged by our particular cosmic address, not by a wild amount, not enough to throw away the whole picture, but enough to remind us that our grand model of everything was built from a very specific vantage point inside one of the least average neighborhoods in existence. Astronomers are careful here. They don't claim that we sit exactly at the center of this void, like some chosen point. The data only suggest that we are comfortably inside it, somewhere within a region whose density slowly rises back toward normal as you move out a few hundred megaparsecs. Beyond that, the universe seems to resume its usual large-scale pattern, filaments, walls, and clusters, filling in like the grain of wood. To probe this more deeply, people turn again and again to simulations and surveys. Vast numerical universes, like the Millennium, Illustris, and Eagle runs, allow cosmologists to watch how voids form and grow over billions of years. They can place imaginary observers in different environments and ask how the cosmos would look from there. Again and again, the pattern appears. Regions with less matter tend to show higher apparent expansion when measured from within. Even relatively modest voids can bias the inferred Hubble constant by a few percent, scale up to a truly huge hollow, and the effect grows stronger. Meanwhile, telescopes like Hubble and the James Webb Space Telescope refine the distance ladder by staring at Cepheid variables and type Ia supernovae in nearby galaxies, measuring their pulsations and explosions with increasing care. But no matter how precise these measurements become, they all share one feature. They are taken from inside the same broad cosmic bubble. It's a bit like trying to decide how flat the ocean is while standing in the trough of a long, slow wave. Everything you see is gently tilted by the part of the wave you happen to occupy. Farther out, beyond the suspected edge of the KBC void, galaxies appear to follow the calmer expansion rate suggested by the cosmic microwave background. Closer in, they seem to be receding just a little faster than that global average. The tension between those two regimes is what keeps the argument alive. Some scientists are convinced that the void alone cannot explain the whole difference. Others think it might be a major piece of the puzzle, layered together with more exotic effects. New instruments are now being built and tuned to test all of this. Euclid, for example, is charting the three-dimensional distribution of hundreds of millions of galaxies, effectively drawing a relief map of the cosmic web and its gaps. Another project, the Dark Energy Spectroscopic Instrument, is measuring how ancient sound waves imprinted themselves on the positions of galaxies, subtle ripples called baryon, acoustic oscillations that serve as a kind of standard ruler. If expansion really varies inside voids, these ripples should look slightly stretched in underdense regions compared to denser zones. Other simulations suggest that even the motion of our own local group of galaxies may be gently influenced by the surrounding emptiness. Matter inside a void tends, over time, to drift outward toward the denser walls. That slow gravitational outflow can push galaxies apart a little faster than the average Hubble flow. If the Milky Way and Andromeda are being carried along by that drift, then our whole neighborhood is riding on a quiet current in the fabric of space. Cosmologists sometimes put it in simple, almost haunting terms. Voids are where cosmic acceleration hides. Not because they are magical, but because in those low gravity zones, the repulsive effect we bundle under the name dark energy has less to fight against. Its influence shows more clearly, like a soft breeze felt more easily in an open field than in a crowded forest. None of this means that the laws of physics we use are wrong. Einstein's equations still describe the same relationship between matter, energy, and the geometry of space-time. Light still bends, clocks still tick, particles still move according to the same rules. What changes is the background on which those rules play out. Our measurements carry the imprint of our surroundings. We are, as one popular phrase puts it, participants in the cosmic experiment, not outside observers. As new data arrive from Webb, from Euclid, from the Vera C. Rubin Observatory scanning the sky night after night, we will see more clearly whether the expansion rate settles back to the cosmic value beyond our bubble, or whether the mismatch persists even there. If the rate slows beyond the boundary of the underdense region, it would be strong evidence that the void is real and locally inflating. If not, then something richer and stranger, perhaps changing dark energy or a gentle modification to gravity itself, may be at work. For now, the picture forming around us is quietly humbling. Every galaxy we map, every standard candle we study, every careful fit of model to data is done from within the same lightly emptied region of space. The emptiness is not dramatic. You would not notice it by looking up with your eyes alone, but across billions of light years, that small difference in density softly tilts our view of time, distance, and age. Even so, the universe remains remarkably consistent. Gravity still gathers, light still travels, orbits still curve, the equations hold. It is only that here, in this particular hollow, the universal note we call expansion rings, a little higher than average, like a string very slightly loosened from the rest. So when you hear about the accelerating universe, about dark energy pushing everything apart, you can gently remember this. The stretch of space we inhabit may be one of the fastest growing pockets in the known cosmos, a quietly over-eager bubble in a larger, more measured web. And tucked inside that thought is a softer, unsettling question, one that hangs in the dim like a low-voiced worry. If gravity is already gentler here, if the pull that knits matter together is slightly weakened inside this void, is there some way in which it can fail more deeply? Could it, in a sense, begin to break inside the emptiness that surrounds us? Out in those hollow reaches of space, the question hangs in the dark like a low note. What really happens to gravity there? Not in the places crowded with stars and clusters, but in the wide, thin stretches where almost nothing lives. There are regions between the great gatherings of galaxies where matter is so scarce that the familiar pull we rely on, the same gravity that shapes stars, binds galaxies, and keeps planets in their paths, can no longer fully set the tone. In those enormous cavities, hundreds of millions, even billions of light years across, another influence quietly takes over. Not a new force we've never heard of, but one that is usually drowned out by gravity's voice: dark energy. When astronomers weigh the universe using missions like WMAP and Planck, they find that almost 70% of everything is this strange, diffuse push we call dark energy. Normal matter, the stuff that makes stars, gas, dust, and you, is only a tiny sliver. Yet, you don't feel dark energy when you lean on a table or stand on the ground, because in dense places, gravity still wins the argument. It pulls, it gathers, it holds. Inside the voids, though, the story bends. There, the thin fog of matter can't pull very hard. Gravity murmurs instead of roaring, and in that softening, dark energy gets room to speak. Space there doesn't just expand with the rest of the universe. It stretches a little more freely, like fabric in a place where no one is tugging back. One cosmologist once put it in a simple, almost lonely way. In the cosmic voids, expansion speeds up because gravity has no one left to talk to. To see this in more than poetry, astronomers map galaxies over huge swaths of sky. When they turn those maps into three-dimensional pictures, the universe starts to resemble a sponge or a tangled web. Long filaments of galaxies and clusters trace out the walls. In between lie the bubbles, the voids. They aren't perfectly empty. A few dwarf galaxies float there. Thin gas threads through, dark matter halos drift unseen. But on average, these regions hold only a fraction of the matter you'd expect from a typical patch of the cosmos. Einstein's equations say that the curvature of space-time depends on how much energy and matter are present. Less matter means less curvature, a geometry that is closer to flat. When you then add dark energy, which in those equations behaves like a uniform pressure built into space itself, that flatter region doesn't just sit still, it accelerates outward. Inside a void, where matter is scarce, that outward push is no longer gently opposed. It takes the lead. That is part of why cosmologists have fallen in love with voids as quiet laboratories. By watching how light from faraway galaxies passes through them, they can test whether dark energy really behaves like a steady background or whether it shifts with environment. Large surveys have traced hundreds of these hollows and measured the tiny distortions they imprint on background galaxies. Behind a heavy galaxy cluster, light is strongly bent and magnified. We call that gravitational lensing. Behind a void, something subtler happens. Because the space inside has stretched more than average, background galaxies can appear just a bit larger and brighter than expected, as if the light has had a little extra room to spread. This gravitational outflow isn't a wind you could feel, but over billions of years, it gently pushes matter from the centers of voids toward their edges, turning each hollow into a slowly inflating bubble. Computer simulations show this beautifully. In these digital universes, filaments pull matter into knots, while the gaps between them widen. As time flows forward in the simulation, the dark spaces swell and merge, until by the present day voids fill almost all of cosmic volume, even though they hold almost none of its mass. The universe becomes a kind of honeycomb, thin, bright walls enclosing vast cells of nearly pristine darkness. Inside those cells, the physics feels almost foreign compared to a busy cluster. The gravitational wells are shallow, so the time dilation you hear about near black holes and massive objects is much weaker. Clocks would tick ever so slightly faster in voids than in crowded regions. Photons, the little packets of light that pass through a large void, can lose a tiny bit of energy as they ride the rapidly stretching space, cooling just a few millionths of a degree. Maps of the cosmic microwave background, the leftover glow of the Big Bang, show subtle cold spots that line up with known supervoids, as if these hollows have left fingerprints on the oldest light there is. One especially large region, sometimes called a supervoid, in the direction of the constellation Eridanus, seems to coincide with a colder patch of the microwave sky, consistent with photons drifting through an area where expansion has run ahead of the surroundings. So does gravity break there? Not in the sense of shattering or disappearing. The equations still hold. The rules don't suddenly change. What shifts is the balance. Below a certain density, gravity can no longer keep pace with dark energy's outward pressure. On small scales, inside galaxies, star systems, and clusters, gravity still rules, folding gas into stars and stars into orbits. On scales of hundreds of millions of light years, especially inside the voids, dark energy takes over, and space itself accelerates outward. Between those realms lies a delicate transition zone. Inside a large void, researchers find that expansion can be noticeably faster than in the surrounding filaments, by something like tens of % in their models. An observer floating in such a region will naturally measure a higher expansion rate than someone deep inside a dense knot of galaxies. It doesn't rip atoms apart or fling planets from their stars. The effect is far too gentle on human scales. But over cosmic time, it quietly reshapes the large-scale scenery, thickening the walls and thinning the interiors, turning the universe into that increasingly stark honeycomb of structure. Even inside these hollows, though, gravity doesn't vanish. Small galaxies still form in isolation, their stars tracing slow, calm spirals. Without frequent collisions and mergers to stir them up, they evolve more gently, with simpler chemistry and cleaner gas. They are like little rural towns, far from the crowded cities of clusters, quieter, less disturbed, but still governed by the same basic rules. Their existence is a reminder that even where matter is scarce, gravity continues its work, only with a lighter touch. Some astronomers like to say that the universe seems to be trying to empty itself out. Gravity pulls matter wherever it can gather it, clumping it into filaments and clusters, while dark energy steadily stretches the spaces in between. Over time, voids merge and grow, and the bright walls between them may thin. Far in the future, the cosmic web we see today could fade into a nearly featureless, cold, accelerating expanse. We are nowhere near that end state yet. For now, gravity still holds firm in stars, planets, and clusters. It still ties the Milky Way into the larger filaments of our supercluster, anchoring us in the web. But inside the wide bubble we call home, it's clear the balance is already tilted. Space here expands a little faster, clocks here drift a little quicker, and light crosses the distances between galaxies just a bit too easily compared to the cosmic average. Every measurement we make carries that quiet fingerprint. From there, another question naturally drifts in. If so much of the universe is made of these hollows, why is there anything at all? If you could somehow gather every atom in the observable universe, every star, every planet, every grain of dust and wisp of gas, and compress it, it would fill only a vanishingly small fraction of the available space. The rest is vast, cold, and almost perfectly empty. Astronomers describe what we see as a cosmic web, a grand framework shaped by gravity over nearly the entire age of the universe. More than 90% of the volume is made of voids. These aren't mere gaps between galaxies. They are the dominant feature. The bright parts, galaxies, clusters, arcs of starlight, trace the threads and walls of this web, like the glowing outlines of a sponge. Our own Milky Way lies on one of these thin threads, a lit bridge stretched across a deep, surrounding darkness. From far enough away, our galaxy would look like an island in an immense black sea. That sea is not full of hidden stars. It is simply space, expanding and almost bare. The way this arrangement came to be reaches back to the universe's first moments. Just after the Big Bang, the young cosmos was astonishingly smooth. Matter and radiation were spread out with almost perfect uniformity, but not perfectly. Tiny fluctuations, minuscule wrinkles in density, were imprinted there, likely born from quantum jitters when the universe was unimaginably small. Satellites like WMAP and Planck have mapped those wrinkles in the cosmic microwave background, capturing a kind of baby picture of the universe when it was only a few 100,000 years old. The slightly brighter and darker patches on those maps mark places where the density was a hair higher or lower than average. By only a few parts in 100,000, that was enough. Over billions of years, gravity magnified those initial differences. Slightly denser regions pulled in more matter and grew even denser, becoming the seeds of the clusters and filaments we see now. Slightly thinner regions did the opposite. They expanded a bit faster, pushing matter outward and becoming the voids. The result is today's architecture. Narrow bands, rich in galaxies, only a few megaparsecs wide, separating enormous cavities that can stretch for hundreds of megaparsecs. When astronomers traced these structures with surveys of millions of galaxies, they saw patterns that looked uncannily like neural networks or branching roots, dense nodes where many filaments meet, and in between, widening chambers of near nothing. This isn't random chaos. It's what happens when simple laws act patiently over unimaginable scales. Computer simulations that build universes in silico reproduce this same pattern when they include dark matter, dark energy, and the rules of general relativity. Voids are not added by hand. They appear naturally as matter flows toward gravity's deeper wells and leaves the rest behind. And yet, the more precisely we look, the more extreme some of these hollows appear. They are larger and smoother than early expectations suggested. The one we seem to inhabit, the KBC void, is a particularly striking example, stretching perhaps 2 billion light-years across. In standard models, such a large underdensity is rare, something you wouldn't expect to see often at all. But multiple surveys, using galaxies, supernovae, and infrared maps, keep hinting that our region really is unusually sparse. That realization has forced cosmologists to rethink what typical means. The average place in the universe is not inside a galaxy, or even near one. It is in the dark silence between them. Emptiness is not the exception, it is the rule. The thin walls and threads of matter are the accents on that emptiness, not the other way around. Voids are not dead, though. They breathe, in their own slow way. As dark energy drives the overall expansion, these bubbles swell and merge. Galaxies within them drift gently toward the surrounding filaments, leaving their interiors ever cleaner. If you could travel outward from the Milky Way, across our local void, you would spend hundreds of millions of years of light travel time crossing regions with almost nothing in them, just the occasional faint galaxy, like a porch light in a vast countryside. New instruments, with eyes sensitive enough to catch these faint systems, are showing that life in a void is different. Galaxies there form stars leisurely. Their gas is less stirred, their histories less violent. They offer yet another kind of laboratory, places where gravity has had very little help from neighbors, so its work can be seen in slow motion. Other missions aim not just to list the voids, but to measure how they change. By tracking their shapes and sizes across cosmic time, scientists hope to learn whether dark energy behaves like a constant pressure or evolves, strengthening or weakening as the universe ages. Voids are also places where the pure geometry of space-time is easiest to read. With little mass to bend light, gravitational lensing is minimal. The paths of photons are straighter. In some cases, light from distant quasars that passes mostly through voids seems to arrive just a touch earlier than you'd expect. If the journey were dominated by heavy structures, a tiny sign that expansion, not attraction, has set the pace. The coldest spots in the microwave sky also tend to align with major supervoids, as though these empty regions have etched their presence onto the first light. It all adds up to a picture where structure is defined as much by absence as by presence. The universe is not just a collection of things, it is the pattern of where those things aren't. And so, when we say the universe is mostly nothing, it isn't a gloomy confession. It's a description of how the interplay between gravity and dark energy has sculpted everything. Gravity gathers matter into shining threads and knots. Dark energy widens the gaps and keeps them from closing. Together they weave the sponge-like cosmos we see in deep images, bright islands and arcs of galaxies, surrounded by immense blackness that is not a camera fault, but the genuine shape of space. In that design, we find our place. a single galaxy on a delicate strand, drifting through an expanding sea of quiet. The voids are not just gaps, they are the other side of structure itself. And in their size, in their emptiness, they carry a gentle warning. If living inside such a bubble truly changes how space stretches around us, if low gravity and fast expansion are the signature of our address, then every number we extract from the sky, the speed of expansion, the distances to galaxies, even the age we assign to the universe, may be tinged by that local bias. Not enough to overturn the story, perhaps, but enough to bend it, which leaves us with a soft, unsettling thought to sit beside you in the dark. If we are measuring the universe from inside a bubble of low gravity and faster expansion, how much of what we call our cosmic truth is really a property of the cosmos itself, and how much is a distortion born from where we happen to live? It's a quietly unsettling thought, isn't it, that simply where we happen to live in the universe might be bending the answers we get when we ask how big it is, how fast it grows, how old it's become? For more than a century, astronomers have leaned on a comforting assumption called the cosmological principle, that on large enough scales, no place is special. The universe, smoothed out over hundreds of millions of light years, should look roughly the same in every direction and from every point. But if our home really lies inside a vast, underdense region, a cosmic bubble billions of light years wide, thinner in matter than average, then that assumption starts to wobble. It doesn't mean the laws of physics are wrong, only that our view of them might be skewed by our neighborhood. In a sense, the universe could behave one way here and slightly differently elsewhere, the way weather feels different in a valley than on a mountain, even under the same sky. When we measure how fast space expands, we usually talk about the Hubble constant, a number that tells us how quickly distant galaxies are receding per unit distance. Close to home, we infer that number using standard candles like Cepheid variable stars and type Ia supernovae objects, whose true brightness we think we understand. We see how faint they look, turn that into a distance, then compare it to how much their light is stretched by expansion. Those candles live in galaxies that are all, in cosmic terms, part of our local surroundings. Every one of them is inside the same broad region defined by the KBC void. If space inside that bubble is stretching a bit more quickly because gravity is weaker here, then the value we get, around 70-something kilometers per second per megaparsec, may not be the true cosmic average at all. It may be our local expansion rate, the tempo of our particular patch of fabric. Far beyond our bubble, we listen to a different kind of messenger, the cosmic microwave background, the afterglow of the Big Bang itself. When missions like Planck fit that ancient light with our best cosmological models, they arrive at a slower expansion rate, around the high 60s. That number represents something closer to the global average, a kind of universe-wide tempo. The mismatch only about 9% on paper, but enormous in terms of implications, is what people call the Hubble tension. To explain it, theorists have dreamed up new particles, exotic forms of dark energy, tweaks to the early universe. But there's also this softer, almost shy suggestion: maybe space isn't as uniform as we assumed. Maybe our part of the cosmic web really is emptier than most, and that emptiness is quietly inflating our local measurements. You can imagine the universe as a network of bubbles and walls. Galaxies gather into filaments and clusters that form the walls. In between, the voids swell like the interior of soap bubbles. In the walls, where matter is dense, gravity pulls hard and slows the expansion. In the interiors, Where matter is scarce, gravity has less to work with, so space stretches more freely. If we happen to live inside one of these faster expanding regions, every standard candle we see will seem to be racing away more quickly than the global norm. Researchers like Seshadri Nadathur and colleagues have tried to quantify this, using large surveys of galaxies and the subtle ripples called baryon acoustic oscillations. They modeled how big, under-dense regions influence what an observer inside them would measure. Their conclusion was quietly dramatic. Large voids can make the expansion appear faster by roughly the same amount as the Hubble tension. The numbers line up better than anyone is entirely comfortable with. The void hypothesis doesn't explain everything, they caution, but it explains a lot. In that light, our physics isn't broken. Einstein's equations still hold, still link matter and geometry with the same steady logic. What changes are the inputs: local density, curvature, and gravitational potential vary from place to place, and that variation feeds into what we see. In a lower density region, space-time is less curved. Light follows slightly different paths. Distances inferred from brightness and redshift shift by just enough to matter. It's like trying to judge the height of waves while standing in a trough. Your entire frame of reference is tilted, and unless you know that, every measurement you make will carry the hidden slant. An observer sitting deep inside a rich galaxy cluster, where gravity is strong and expansion slowed, would reconstruct the universe's history with subtly different numbers than we do out here in our airy bubble. Astronomers know this now, and they're careful. Teams working on supernova cosmology and distance ladders openly acknowledge that the tension is real, not a mirage of sloppy data. As the measurements get more precise, the discord doesn't vanish, it sharpens. Missions like Euclid are being built specifically to map how density and expansion change across space and time. By charting over 1 billion galaxies, they will test whether voids truly expand faster and filaments more slowly, and how strong that environmental dependence really is. There's another, more delicate effect layered on top: gravitational redshift. Light climbing out of a deep gravitational well loses a bit of energy and shifts toward the red. Light traveling mostly through emptier regions loses less, arriving slightly bluer than expected. If we live in a place where gravity wells are on average shallower, then photons reaching us from dense regions carry a subtle bias. That bias can ripple into our distance calculations, nudging our estimates of how fast the universe expands and how far its landmarks really are. Because of all this, cosmologists no longer trust any single method alone. They cross-check supernovae with baryon acoustic oscillations, with weak lensing distortions of galaxy shapes, with counts of galaxy clusters, with temperature patterns in the microwave background. Each probe responds differently to density variations, and by comparing them, they can tease out how much of our picture is truly universal and how much is tinted by our location. Even the cosmic microwave background bears the signature of voids. When those photons pass through a big, fast-expanding hollow, they lose less energy than when they pass through heavy clusters, leaving behind faint cold spots in the temperature map. Those cold patches line up suspiciously well with known supervoids, hinting that the universe is indeed full of regions where expansion runs a little ahead. If that's the case, then a lot of what we treat as universal might actually be local habit. Our best estimate of the universe's age, about 13.8 billion years, comes from fitting expansion histories to the data we see from here. If our corner of space is stretching faster than average, those fits bend toward a younger age. Some analyses suggest that, from the global perspective, the universe might be closer to something like 12+ billion years old instead. And yet we see very old things. Ancient star clusters whose ages seem to rub uncomfortably close to the upper limits we've allowed, as if they are quietly telling us that our timelines need adjusting. The James Webb Space Telescope has already found bright, surprisingly mature galaxies when the universe was only a few 100 million years old. By our current reckoning, objects that force cosmologists to squint at their models and wonder if distances, ages, or growth rates have been nudged by the environment we observe from. Some astronomers phrase it gently. We may not be seeing the universe as it is, only as it looks from here. The physics underneath remains sound, but our viewpoint is not neutral. We are embedded in one of the Webb's more extreme features, and that fact must now be part of any precise story we tell about cosmic history. So, could living in a void make our physics wrong? In one sense, yes. It can make our measurements wrong and our interpretations skewed. It forces cosmology to grow more local, to account for position-dependent effects rather than relying entirely on global averages. That is why the next generation of observatories, Rubin scanning the sky, Euclid mapping structure, Webb peering deep into time are so important. Together, they will help separate what truly belongs to the universe, everywhere, from what belongs to our bubble alone. Because if the KBC void is real and expanding faster than the rest, then every constant, every distance, every age we've inferred carries a faint watermark. You measured this from inside an underdense, overeager pocket of space. And once you've noticed that, another question naturally rises, one that feels almost like a contradiction wrapped in a lullaby. We've been saying that gravity pulls, that it gathers matter and sculpts structure, but inside these emptying hollows, the motion of galaxies can look as if gravity is doing the opposite, almost as if it's pushing. In the simplest textbooks, gravity is always attractive. The quiet architect drawing planets toward stars and stars toward galactic centers. Yet when astronomers trace the movements of galaxies inside large voids, they don't see them falling inward. They see them drifting outward, away from the emptiest regions and toward the denser walls of the cosmic web. It's as if every galaxy in a void is rolling gently down an invisible slope, heading for the bright filaments that frame the darkness. The key is not that gravity has changed its nature, but that its geometry has flipped. Gravity responds to differences in mass, to contrasts. In a cluster where matter is piled up, the net pull points inward. In a void, the denser stuff is outside. An object floating inside such a hollow feels more pull from the distant walls than from the sparse interior, so the net tug is outward, toward those walls. The force is still attractive, it's just attracting toward the edges rather than the center. Cosmologists who map our local universe see this pattern clearly. Using catalogs of galaxy distances and velocities, they reconstruct the flow of matter over hundreds of millions of light years. The maps show galaxies near void centers drifting away, while those near filaments fall toward the bright spines of the web. Each void behaves like an inflating bubble. Its interior thins, its boundary sharpens, and galaxies inside are gently carried outward by a combination of gravitational imbalance and faster expansion. Surveys of redshifts over huge areas of sky back this up. When you plot the peculiar motions, those little deviations from the smooth Hubble expansion, you find that the motion lines fan out from voids and converge on filaments and clusters. Space is not just stretching uniformly, it's also rearranging, sliding matter from the hollows into the walls. At first glance, it sounds like gravity has turned repulsive, But that's not what's happening. Inside an underdense region, there's simply less gravity to slow expansion. General relativity says that in areas with lower density, the deceleration due to gravity is weaker, so the expansion that dark energy drives can run more freely. The result is an interior that grows faster than its surroundings. From inside, that extra stretch adds on top of the usual Hubble flow, making galaxies appear to flee the void's center faster than expected. Computer simulations, those digital universes where scientists can fast-forward billions of years in a few hours, show this behavior beautifully. Regions that start slightly underdense expand more quickly. Their boundaries sharpen, their interiors empty out. Matter travels outward at speeds of a few hundred kilometers per second relative to the void centers, piling up in sheets and filaments. Gravitational outflow, they call it. Not gravity pushing, but gravity and expansion combining to lift matter out of the hollows. We see the fingerprints of this outflow in many places. In specific supervoids, galaxies near the edges move outward relative to the center with measurable extra speed. In our own neighborhood, the large-scale motion of the Laniakea supercluster appears to be shaped by both a pull toward massive structures like the Shapley concentration and a kind of gentle shove from the underdense region behind us, the local void. One side tugs, the other side lets go. Our path through space is set by both. All of this feeds back into the Hubble tension too. An observer inside a region where galaxies are already drifting outward faster than average will, if they simply fit a straight line through distance and velocity, infer a higher expansion rate than someone in a quieter patch. The gravitational outflow of voids becomes another way our local environment sneaks into the numbers we write down in textbooks. Even the oldest light carries traces of this dance. As microwave background photons cross expanding voids, they lose a bit of energy differently than they do traversing clusters, leaving tiny, cool spots in all sky maps. Those cold patches line up with known large voids, confirming that emptiness is not a passive backdrop, but an active player. In the end, gravity is not broken inside the voids. It hasn't turned into a new force. It is simply doing what it always does, responding to the distribution of matter while dark energy quietly pushes on the overall fabric. The result looks strange to our intuition. Galaxies in hollows drifting outward, walls collapsing inward, the cosmos breathing in a complex rhythm of collapse and expansion. It's humbling to realize that the same force holding your feet to the floor is also guiding entire superclusters along these vast flows, sometimes pulling, sometimes relaxing its grip. The universe is not static. It inhales where matter is rich and exhales where matter is scarce. The voids are part of that long, slow breath, their outflow helping to set the tempo of cosmic growth. And tucked inside that realization is yet another question, soft but profound. If expansion really does speed up in the emptiest places, if our entire local region is riding one of those faster currents, then what does that do to the story we tell about how long the universe has been unfolding? If expansion inside the voids is quietly accelerating our corner of the cosmos, then could our entire measurement of the universe's age be wrong? It's a strange thought to cradle at the edge of sleep. What if the universe has been quietly misleading us about its age, not with malice, just with geometry and perspective? For decades, the number 13.8 billion years has sat like a calm anchor in our minds. It comes from careful fits to the faint afterglow of the Big Bang and to how fast space appears to be stretching. It feels solid, settled, almost comforting. But if we trust the faster expansion rate measured in our cosmic neighborhood, that anchor slips running the clock backwards from that higher rate, the universe seems to have had less time to get from the Big Bang to now closer to about 12.7 billion years. On paper, the gap is only around a billion years. In practice, it tears at the seams of our story, because some of the oldest stars we know are already pushing up against that younger age. Take ancient globular clusters around the Milky Way, and stars like the so-called Methuselah star. When astronomers use stellar evolution models and exquisite parallax measurements from missions like Gaia, they find ages around 13 billion years for some of these elders. If the universe were truly only 12.7 billion years old, those stars would be older than the cosmos that birthed them. That can't be right. Either our stellar clocks are off, or our cosmic calendar is. To untangle this, cosmologists hold two yardsticks side by side. One is local, nearby supernovae, Cepheid variables, and redshift measurements within a few hundred million light-years. That path leads to a higher expansion rate and a younger universe. The other is global, the ripples frozen into the cosmic microwave background, mapped down to tiny temperature differences by satellites like Planck. That path points to a slower expansion and the familiar 13.8 billion year age. Both approaches use good physics. Both are built on decades of refinement. Yet, they do not agree. This quiet conflict has earned a dramatic name: the cosmological age crisis. It is like listening to two clocks that were built by the same watchmaker and discovering they refuse to tick in sync. Somewhere between those clocks sits our own cosmic address. If, as many lines of evidence now suggest, we live in a large, underdense region, a void, then our measurements from here could naturally push the local clock to run differently. With less matter around, to slow expansion, space in our neighborhood might be stretching faster than the cosmic average. That would make galaxies look closer in time than they really are, and the inferred age of the universe seem too young. In that case, the older, 13.8 billion year figure from the microwave background might still be closer to the truth, and the apparent youthfulness a trick of our vantage point. If the void effect isn't enough to close the gap, though, something deeper may be stirring. One possibility is that dark energy, the mysterious pressure that drives cosmic acceleration, is not constant after all. Einstein treated it in his equations as a fixed term, an unchanging property of space itself. But it might evolve, growing stronger as the universe expands. If that's true, the expansion could have been slower in the past and faster now, bending our age estimates in subtle ways. Missions like Euclid have been sent up precisely to look for signs of this, by mapping how galaxies cluster and how voids grow at different epochs. They trace the strength of cosmic acceleration over time. If dark energy's push changes, that would ripple through every timeline we've drawn, from the cooling of the early plasma to the birth of our own Sunday. At the same time, the James Webb Space Telescope is peering back to extraordinary redshifts, catching light from galaxies that lived when the universe was only a few 100 million years old by our current reckoning. Many of those systems look surprisingly grown up, massive, bright, rich in stars. If the universe is younger than we think, or if structure took longer to form, their existence becomes even harder to explain. It's like walking into a nursery and finding not infants, but fully formed adults, waiting there, quietly insisting that they had time to grow. Faced with this, some theorists sketch out hybrid ideas. Perhaps there was a brief, early phase where dark energy behaved differently, letting structure form quickly, while still preserving the overall age. Others play with gentle modifications to gravity on large scales, letting expansion behave one way in low-density regions like ours, and another way in denser parts of the cosmic web. These models live in supercomputer simulations where virtual universes can be rewound and replayed until they resemble what we see. And yet, under all the complexity, the simplest explanation still feels the most hauntingly human. Maybe the universe is not lying at all. Maybe we are simply misunderstanding what it means to measure from here. Einstein's relativity already tells us that the flow of time depends on gravity. In regions with less mass, clocks tick a little faster, distances stretch a little farther, expansion feels a little stronger. If we reside in one of those regions, a large, thinning bubble, then our rulers and clocks might all be slightly slanted. In that picture, the universe is not deceiving us. It is reminding us that context matters. Time does not flow identically everywhere. Space does not expand at precisely the same rate in every corner. Our numbers are not wrong, so much as they are local. For now, the crisis stays unresolved. The most sensitive instruments we've ever built, Hubble, Planck, Webb, Euclid, disagree by just enough to unsettle us and not enough to be dismissed. The universe, as someone once said, is under no obligation to make sense to us. Perhaps it is this sliver of uncertainty, this stubborn mismatch, that keeps astronomers awake long after their telescopes have closed for the night. And out of that unease, another, deeper question rises. Have we been too quick to assume that the universe is the same everywhere? For more than a century, the quiet backbone of cosmology has been the cosmological principle, the idea that if you zoom out far enough, the universe looks homogeneous and isotropic, uniform in every direction and at every point. It was a simple way to honor the notion that no observer on no world occupies a privileged position. Einstein leaned on it when he first applied his equations to the cosmos as a whole. Every standard cosmological model since has done the same. But the suspected existence of the KBC void presses a thumb into that smooth picture. When Ryan Keenan, Amy Barger, and Len Cowie analyzed galaxy surveys and supernova distances, they found that the region around the Milky Way, stretching roughly 2 billion light-years, seems to contain about 20% less matter than average, not a small, local pothole in the cosmic road, but a yawning underdensity on scales where everything was supposed to have smoothed out. Under our current standard model, the lambda CDM model of a universe filled with dark energy, lambda and cold dark matter, CDM, matter distribution, is expected to become fairly uniform once you average over distances of a few 100 million light-years. Clusters, filaments, and voids are all there, but they balance into something statistically even. A void as large and as deep as the KBC region strains those expectations. In many simulations, the odds of finding oneself inside such a cavity are tiny, like winning a cosmic lottery you never bought a ticket for. If we really do live in such an underdense pocket, it means the universe is not as uniform on large scales as we've been assuming. Our position would be special, not in a mystical sense, but in a statistical one. We would occupy one of the rarer environments the universe offers, and that alone would be enough to skew our view of its global behavior. Some try to soften this by pointing to cosmic variance, the unavoidable fact that we only get to observe one universe from one vantage point. Maybe we simply ended up in an unusual region by chance, they say, a slightly odd patch in a sea that is overall homogeneous. But when simulations under standard assumptions struggle to produce voids as extreme as ours, even after many runs, the discomfort grows. Others wonder if dark matter, the invisible scaffolding on which galaxies hang, might be more irregular than we thought on ultra-large scales. If those dark filaments and clumps are uneven beyond our current horizon, perhaps what we see is only a small part of a much messier pattern, and the cosmological principle is an approximation that never really held perfectly. If that's the case, then cosmology as we practice it changes shape. Instead of a single global model neatly describing everything, we may need to admit that different regions of the universe follow slightly different expansion histories, depending on their local mix of matter, curvature, and dark energy. Our theories would need to become more like a patchwork, stitched together from overlapping domains, rather than a single smooth sheet. This is part of what missions like Euclid and instruments like the Dark Energy Spectroscopic Instrument are designed to test. By mapping the positions and motions of millions or billions of galaxies, they can check whether the large-scale structure beyond our neighborhood remains statistically uniform or whether big variations persist. If the universe looks systematically different in different directions or at different depths, the cosmological principle may have to be demoted from a foundational truth to a useful approximation. James Webb adds a more distant layer to the picture. By staring deep into the past, it sees galaxies that formed when the universe was still very young. If those early galaxies are arranged in a way that is more clumped, more uneven than our models predict, it suggests that the seeds of today's giant voids were planted very early on, perhaps by tiny quantum fluctuations stretched by inflation into large-scale quirks. All of this leaves cosmologists with a quiet unease. So much of their work assumes that our view from Earth is not special, that what we see is a fair sample of the whole. If that assumption fails, every distance, every age, every expansion rate tied to it may need to be checked against where exactly it was measured from. Some writers put it starkly: if we are inside a giant void, then much of what we infer about the universe, its rate of expansion, its overall geometry, even its fate, could be colored by that fact. Not completely wrong, but bent in ways we haven't fully accounted for. Of course, the universe had to get this way somehow. Huge voids don't simply appear. They grow out of tiny initial imperfections, quantum fluctuations during the very early inflationary phase could have laid down the seeds for supervoids like ours. Rare, but not impossible. Over billions of years, gravity would have amplified those seeds, pulling matter away from some regions and into others, sculpting the honeycomb we see today. Yet even with that story in hand, the KBC void's size and depth still press against the edges of what our standard models comfortably allow. That tension nudges some researchers to consider more radical possibilities. Perhaps gravity behaves differently on the very largest scales, or perhaps dark energy itself is not perfectly smooth. Either way, our apparent location inside such an unusual structure forces a kind of reckoning with Einstein's old principle. Maybe it was a good description of the early universe, when everything was smoother, and only an approximation of the world we inhabit now, a cosmos that has had time to grow lopsided, with vast regions expanding a little faster than others, like great lungs, breathing at different rhythms. If so, the KBC void might be one of those lungs, inflating quietly, distorting our measurements and challenging the belief that we occupy no special place for the moment. The evidence is suggestive but not final. Future maps from Euclid, the Rubin Observatory, Webb, and other instruments will sharpen the picture, telling us whether the cosmological principle still deserves its central place or whether it must be gently set aside. Because if we truly are breaking Einstein's rule, If the universe is not the same everywhere on the scales we once believed, then we're left with an even more basic mystery to keep us company in the dark. If our universe is no longer uniform, if great voids like ours really exist, and matter has flowed away from them for billions of years, what started those emptinesses in the first place? Out in the dark, when you follow the story of these great hollows far enough back, it leads you to a place almost impossibly small. The idea is quietly outrageous, that the largest structures in the universe, voids billions of light years across, were seeded by ripples smaller than an atom. In the first flicker of its existence, in a time so brief, we can only write it as a power of 10 and whisper it about 10 to the power of negative 35 seconds after the beginning. The universe is thought to have passed through a phase we call inflation. In that instant, space itself swelled at a staggering rate, faster than light could cross even the tiniest distance. While that was happening, the quantum world left its fingerprints. Even empty space isn't truly still. Quantum fields tremble with tiny, random fluctuations in energy. Under normal conditions, those jitters appear and fade almost at once, like ripples on a pond that never quite form a wave. But inflation grabbed those microscopic uncertainties and stretched them until they spanned whole regions of the young universe, places that, by pure chance, had slightly more energy or slightly less. Later, long after inflation ended and the universe cooled into a glowing fog of plasma and light, those stretched out ripples were still there, encoded as tiny differences in density. When NASA's WMAP and ESA's Planck satellites mapped the cosmic microwave background from the afterglow, from when the universe was only about 380,000 years old, they saw them as faint speckles of slightly warmer and cooler patches, only one part in 100,000. To the eye, they look like soft grain in a photograph. To cosmologists, they are the blueprint of everything. The slightly denser spots would one day grow into clusters, filaments, and superclusters. The slightly thinner spots would become the deserts, the cosmic voids. It's almost impossible to wrap your mind around a region that, back then, was only 0.1% less dense than its surroundings can. After billions of years of expansion and gravity, turn into a cavity like the KBC void around us, 2 billion light-years wide and noticeably emptier than average, a barely audible murmur of quantum noise, stretched by inflation, becoming an enormous silence in the cosmic web. Inflation theory, first sketched by people like Alan Guth, rests on quantum field theory, the idea that even in a vacuum, fields can fluctuate. The hypothetical field that drove inflation would have done just that, bubbling in energy from place to place. When inflation stopped and the universe reheated, those frozen patterns in the field became patterns in matter and radiation. Where the energy had been a touch higher, matter would later collect and expansion would slow. Where it had been a touch lower, matter would be scarcer and expansion would run a little freer. In computer simulations, cosmologists start with ripples like the ones Planck measured in the microwave background. They let dark matter respond to gravity over billions of years, with normal matter, gas, dust, stars following along. What emerges on their screens is a universe that looks eerily like the one we see through telescopes, bright filaments of galaxies wrapping around huge, gently rounded voids. Both the crowded knots and the empty pools trace back to the same simple origin: quantum fluctuations magnified by inflation. That connection between the smallest realm we know how to describe and the largest structures we can see is one of the quiet marvels of modern science. The uncertainty that rules particles turns when stretched across space and time, into the geometry of clusters and the shapes of the gaps between them. The structure around us is, in a sense, fossilized quantum noise, but nothing we measure is perfectly even. When Planck looked more closely at the microwave background, it found something slightly odd. One half of the sky seems just a little smoother and cooler than the other. It's a tiny effect, easily lost in the numbers, but persistent enough to make theorists frown. If those earliest ripples were not perfectly random, if they carried some built-in tilt or directionality, then the seeds of today's supervoids might have been laid down in a way our simplest models don't capture. Experiments at the South Pole and elsewhere are now listening for another echo of that first instant, a delicate twist in the polarization of the microwave background that would betray primordial gravitational waves. These ripples in space-time, if they exist, would be direct proof that inflation really did shake the universe in the way we think, and that quantum fluctuations didn't just sculpt matter, but also stirred gravity's first heartbeat into the fabric of reality. Closer to our own time, missions like Euclid and telescopes like the James Webb Space Telescope look at the problem from the other end. Instead of staring at the baby picture of the cosmos, they watch how voids and filaments behave today. If the sizes, shapes, and growth of these empty regions match what inflation, dark matter, and general relativity predict when combined with those initial ripples, it strengthens the idea that quantum noise really did whisper the pattern of everything to come. When you think about the KBC void in that light, it becomes even stranger. This immense, cold, underfilled volume through which our galaxy drifts on a delicate thread may have started as a fluctuation smaller than a proton, a slightly lighter patch in the primordial field. Over nearly 14 billion years, gravity gathered matter elsewhere, leaving this region thinner, quieter, more eager to expand. We now float in that magnified whisper, surrounded by a desert that was scripted at the universe's birth. It is a powerful story. Randomness at the tiniest scales, order and pattern across the largest. But if quantum fluctuations and gravity together drew the outlines of the cosmic web, there is still a question lingering at the edges. Are those two ingredients enough to explain what we actually see? Or is there something deeper, some additional rule or field or symmetry, quietly guiding how far emptiness can go? Gravity, as we know it, is the main architect in this story. Over almost 14 billion years, it has pulled matter into the filaments and nodes that make up the visible skeleton of the universe, leaving nearly 90% of the volume in between as low-density voids. On paper, under Einstein's equations and our standard lambda CDM model, that process should produce a web that, when you zoom out far enough, looks statistically smooth, varied in detail, but well-behaved on the largest scales. Yet observations keep nudging at the edges of that comfort. Supervoids like the one we inhabit, or like other enormous underdense regions mapped in galaxy surveys, seem surprisingly deep and wide compared to what many simulations produce when they use only our usual ingredients: dark matter, dark energy, and general relativity. In many modeled universes, voids this extreme are possible, but very rare. The fact that we appear to live in one of them has become another quiet tension. To test whether gravity, as we currently describe it, can really account for this, cosmologists run ever larger and more detailed simulations. Projects like Illustris TNG evolve billions of particles representing dark matter and gas, letting them interact under Einstein's rules as the universe expands. They do a beautiful job of reproducing many features we observe: the distribution of galaxies, the sizes of typical voids, the way clusters grow. But voids with the exact combination of size and depth that we infer for our region remain out on the tail of what those virtual universes tend to produce. That doesn't mean gravity is wrong. It might mean we haven't yet captured every subtlety of how inhomogeneities, lumps, and gaps feed back into the overall expansion. Relativity is a non-linear theory. In a universe full of clumps and holes, the average behavior is not always the same as the behavior you'd calculate for a perfectly smooth fluid. This idea, sometimes called back reaction, suggests that the patchwork nature of the cosmos could, in aggregate, make expansion and structure formation behave slightly differently than our simplest averaged models predict. There are also more adventurous possibilities. Some alternative theories adjust how gravity works in environments of very low density, making its pull fall off differently inside voids than in clusters. Others add new fields that couple to curvature, gently modifying how space-time responds to matter on the largest scales. These ideas are still speculative, and each comes with its own challenges. They must match the exquisite precision of the microwave background, the behavior of galaxies, and countless other tests where general relativity has succeeded, rather than throw Einstein away. Most cosmologists treat these tensions as stress tests. They build better simulations, gather deeper galaxy maps, and search for places where gravity's predictions and the sky diverge in a clear, consistent way. Instruments that measure weak gravitational lensing, the subtle stretching of galaxy shapes by intervening mass, offer one of the sharpest tools for this. If light bends through voids and filaments in a way that systematically departs from expectations, it would be a sign that something in our description of gravity or dark energy needs revisiting. So far, gravity explains nearly everything we see, but not quite everything. The largest voids, the small anomalies in the microwave background, the unexpectedly rapid appearance of structure in the early universe, all of these are gentle hints that there might be more to the cosmic architecture than a simple story of quantum ripples and Einsteinian collapse. From our vantage point, inside a vast underdensity carved from those ancient fluctuations, it's hard not to wonder. The web of galaxies and the oceans of darkness between them form a pattern almost too grand to fully grasp. Whether it is purely gravity's masterpiece or shaped by deeper, still hidden laws, we don't yet know. What we can say is that if gravity alone struggles to explain the most extreme hollows, if simulations and observations continue to disagree about how empty can be, then the universe may be quietly pointing us toward a new chapter, physics, a reminder that even after a century of general relativity, there are still questions hanging in the dark, as soft and insistent as a whisper. If gravity by itself cannot quite account for the voids, what hidden law of nature allowed such impossible emptiness to exist? If these vast hollows really are so hard to explain, a quiet, daring thought begins to drift in. What if the force we trust most in the universe isn't telling us the whole story? For more than a century, Einstein's general relativity has worked with almost eerie perfection. It explains Mercury's odd orbit, the bending of starlight around the sun, the slow whirl of matter near black holes, even the ripples in space-time from colliding neutron stars. On the scales we can probe directly, planets, stars, galaxies, it has never truly failed us. But when we zoom out to the widest scales we can see, stretching over billions of light years, the picture becomes less settled. Inside underdense regions like the KBC void, galaxies seem to drift apart a little faster than our standard simulations predict. These voids are larger, emptier, and more eager to expand than the average universe we compute on supercomputers. To account for that, some physicists have started asking a dangerous question in a very calm voice. What if gravity doesn't follow exactly the same rules everywhere? What if Newton's and Einstein's laws are beautifully accurate approximations of a deeper, more flexible force? All of those ideas live under the umbrella of modified gravity. One of the best-known examples is MOND, modified Newtonian dynamics. It was originally proposed to explain why stars in the outer parts of galaxies orbit faster than the visible mass would allow. In MOND, when accelerations become extremely small, as they do far from galactic centers or deep inside cosmic voids, gravity doesn't weaken as quickly as in standard theory. It hangs on a little more strongly, as if reluctant to let go. If that kind of behavior is real, its influence wouldn't stop at the edges of galaxies. In regions where matter is thin and gravitational accelerations are tiny, a slightly stiffer gravity could help structures grow differently and let the spaces between them deepen in unusual ways. Vast voids like the one we inhabit would be less surprising in a universe where gravity softens and stiffens gently with environment. Of course, MOND, by itself, isn't a full replacement for Einstein. It doesn't naturally include curved space-time or the speed of light as a cosmic limit. To bridge that gap, theorists have built relativistic cousins where gravity arises not just from the curvature of space-time, but also from additional scalar or vector fields. In these models, the behavior of gravity becomes mildly environment-dependent. In dense regions, they closely mimic general relativity. In the thin air of cosmic voids, subtle differences appear. Those aren't just mathematical games. Large galaxy surveys, weak lensing maps, and measurements of how galaxies flow through space are slowly turning into direct tests of gravity on cosmic scales. By measuring how much light bends around clusters and through voids, and how galaxies deviate from the smooth Hubble expansion, we can quietly ask the universe whether Einstein's equations still tell the full story when space becomes almost empty. So far, general relativity continues to pass most of these tests. But at the margins inside the biggest voids, in the faintest distortions, small tensions appear. Some voids lens light a bit less than expected, or seem to expand slightly faster than standard models predict. Those differences might be noise, they might be systematics, or they might be the first hints that something in our description of gravity, or in the properties of dark energy, needs a gentle correction. Many cosmologists remain cautious. Modified gravity models have their own difficulties. Some struggle with galaxy clusters, others with the fine patterns in the cosmic microwave background. The standard lambda CDM picture, with dark matter and dark energy, plus Einstein's gravity, still explains more data with fewer assumptions. But the persistence of alternatives, refined, adjusted, tested again and again, shows how uneasy we still are about stitching together gravity's behavior on small scales with its behavior across the entire cosmic web. And perhaps the most interesting thing about these theories isn't the exact equations they propose, but where they suggest we look. A number of physicists have pointed out that if gravity ever does deviate from Einstein's law, it probably won't reveal itself near the sun, or even around black holes, where we've already tested it to exquisite precision. It will show up in the places we've hardly examined at all, the dark, quiet distances between galaxies, where almost nothing tugs back, and dark energy is free to do as it likes. If future observations confirm that in regions like the KBC, void gravity really does behave differently, even by 1% or 2%, the consequences would ripple through all of physics. We wouldn't be throwing out Einstein so much as expanding him. His theory would remain beautifully correct in our local neighborhood, but incomplete as a description of the entire universe. The cosmos would no longer be governed by a single, simple, gravitational rule, but by a layered set of behaviors that shift gently with environment, density, and scale. It's a thrilling, unsettling idea that the most universal force we know might not be truly universal after all. That in the very emptiness we once wrote off as uninteresting, new laws could be quietly at work. From there, it's natural for the mind to drift to gravity's silent partner in the story of voids, dark energy. For years, we've used that name as a placeholder for everything we don't yet understand about the universe's accelerated expansion. In the simplest version of our models, dark energy is treated as a cosmological constant, a fixed, uniform pressure built into the fabric of space that pushes it to expand faster and faster. But if space itself is not uniform, if enormous voids or vast pockets of unusually low density, it's hard not to wonder whether dark energy really behaves the same way everywhere. The measurements that tell us the universe is accelerating are real, but they come from different epochs and environments. The expansion rate inferred from the cosmic microwave background is not quite the same as the one inferred from nearby supernovae. That tension might be telling us that dark energy is not a rigid constant, but something more like a field that can evolve and respond. If dark energy is dynamic, if it can change its strength over time or vary slightly from place to place, then the emptiest regions would be the most natural laboratories inside a void, where matter is scarce and gravity's pull is weak. Any outward push from dark energy would face less resistance. Space there would stretch more freely, like dough rising fastest where it's thinnest. Large surveys of voids already hint at this. When astronomers measure how quickly galaxies move apart inside these hollows and compare it to the predictions of a strictly constant dark energy, they sometimes see a small excess, a slightly faster local expansion. It's not a dramatic difference, just a few percent, but over billions of years and billions of light years, that small extra stretch can carve noticeably larger, emptier bubbles. Theoretical models that treat dark energy as a scalar field, a kind of cousin to the Higgs field, naturally produce this behavior. In those pictures, the field's value, and therefore its effective pressure, can shift depending on the local environment. In dense clusters, the field may be pinned and quiet. In flat, low-density voids, it can relax toward a different state, increasing the local acceleration of expansion. Slowly, patiently, that differential push writes itself into the geometry of the universe. Cosmologists are now building high-resolution simulations that compare these two possibilities side by side. In one set, dark energy is strictly constant. In the other, it is allowed to vary gently with curvature or density. Both start from the same initial fluctuations measured in the microwave background. Then they watch how the cosmic web unfolds. If the version with dynamic dark energy reproduces the size, shape, and growth rate of real voids more faithfully, it will be a powerful clue that the constant in our equations has been quietly breathing all along. In that light, the KBC void around us takes on a different feel. It's no longer just an awkward statistical fluke. It becomes a place where dark energy might be especially free to act, stretching space a little more eagerly than in denser regions. To observers like us, sitting inside, that would be indistinguishable from a universe that's younger or expanding faster than it really is. Part of the Hubble tension could simply be the echo of the hollow we happen to float within. Some astrophysicists describe it in a phrase that sticks. If dark energy is the universe's breath, then voids are where it breathes the most. In those regions, space pulls itself apart more boldly, and time itself may flow with a slightly different cadence. The numbers we read off the sky carry the faint imprint of that difference. Seen this way, cosmic emptiness stops being a dead backdrop. Voids become active stages where gravity and dark energy reveal how subtle they really are. They're where our standard models are stretched to their limits, where modified gravity and evolving dark energy have the best chance of leaving a clear mark. If, in the years ahead, observations confirm that inside voids, dark energy is stronger or gravity is altered, we'll be faced with a strange new picture. Superclusters and great walls of galaxies, not locked in a perfectly rigid web, but drifting slowly through bubbling pockets of space, nudged by denser regions on one side and pushed by the amplified breath of dark energy on the other. In a universe like that, the thought becomes hard to shake, soft and persistent as a lullaby at the edge of sleep. If dark energy can truly change with environment, if gravity itself bends to context, then could an entire supercluster Laniakea and everything in it be quietly floating inside a void, carried along by the uneven pull and push of the universe's own expanding heart? If dark energy can breathe differently in different places, if gravity itself seems to respond to emptiness, it's hard not to wonder about the thing we live inside of, our own supercluster. What if everything familiar, the Milky Way, Andromeda, the Virgo cluster, tens of thousands of other galaxies, were not anchored in some solid cosmic framework, but drifting together inside a vast hollow of space? Astronomers call our wider home Laniakea. It's an enormous region, about 500 million light-years across, containing on the order of 100,000 galaxies and a mass equivalent to something like 100 million trillion suns. For a long time, people imagined superclusters as big, roughly fixed piles of matter. But when researchers traced how nearby galaxies actually move, the picture changed. In 2014, R. Brent Tully and Hélène Courtois used measurements of redshift and peculiar velocity, how galaxies deviate from the simple Hubble expansion, to map the local flows of more than 8,000 galaxies. They found that all of these systems, including our own, belong to one enormous basin of motion. The galaxies don't orbit a single center. Instead, they stream along curved paths, drawn toward denser regions like the Great Attractor, and gently pushed away from a nearby underdense patch known as the local void. Laniakea isn't defined by where the galaxies are, it's defined by how they move. When that flow map was compared with large-scale density maps from galaxy surveys, an unsettling realization emerged. The whole of Laniakea, along with neighboring structures, appears to sit inside a much larger, underdense region, an extended valley in the cosmic landscape, roughly 2 billion light-years across. The KBC void, our supercluster, is like a bright ridge lying inside a broad, shallow bowl. At first glance, that sounds contradictory. How can something as massive as a supercluster exist inside a region that's missing matter? The answer comes from how the cosmic web actually looks. Voids are not perfectly empty. Even inside them, thin filaments of dark matter and faint strings of galaxies thread across the darkness. Laniakea seems to be one of those strands, a coral reef rising from the floor of an abyss, surrounded not by solid land, but by a deep ocean of thinning space. On average, The universe contains only a few particles in each cubic meter of space. Inside the KBC void, that already sparse density appears to drop by around 20%. It's not a pure vacuum, just a little thinner, a little lighter. That is enough to change the balance between gravity and expansion. Gravity along the filament still binds galaxies together, wrapping them in overlapping halos of dark matter so they don't drift apart. But the surrounding space, being underdense, stretches more freely. Laniakea becomes an island of order, floating in a sea that is subtly rising. You can sense this in our own motion. The local group, the small collection that includes the Milky Way and Andromeda, is not sitting still. Relative to the cosmic microwave background, we're drifting at a few hundred kilometers per second, sliding toward denser regions like the Shapley concentration, while leaning away from the local void behind us. Our entire supercluster participates in this flow, as if it were a luminous raft carried along by currents in the fabric of space-time. Seen from inside, that motion is invisible. The night sky feels still. But when astronomers stack up galaxy distances and velocities, a pattern emerges. We are not at rest in some neutral ocean. We are moving through a valley, falling gently down one side, rising out the other, all while the valley itself broadens as the void expands. That motion may be one of the reasons our measurements of the universe's expansion look the way they do. If Laniakea is floating inside an underdense region where space is already stretching a little faster, then any attempt to measure the Hubble constant from within will naturally give a higher number than the global average. It's like trying to judge the calmness of the sea while surfing on the leading edge of a swell. Simulations that place observers inside large voids show exactly this effect. Local expansion rates can be boosted by several percent compared to the cosmic mean. Not enough to rewrite all of physics on their own, but enough to contribute to the stubborn gap between the value of the Hubble constant inferred from early universe light and the value we measure nearby with supernovae and standard candles. Part of the tension may simply be perspective. We are taking measurements from inside a moving, rising lab. What's remarkable is that, despite the faster expansion around it, Laniakea holds together. Its galaxies share a coherent flow, their motions sculpted by invisible filaments of dark matter, reaching across tens of millions of light-years. Dark energy stretches the fabric, but dark matter glues the structures, letting islands like ours persist even as the ocean deepens. And we are not alone in this arrangement. Deep observations with telescopes like the James Webb Space Telescope have begun to reveal galaxy groups in the distant universe that seem to live in early versions of voids, massive but isolated, surrounded by relative emptiness. Islands and reefs in a dark sea are not a local accident. They are part of the universe's way of organizing itself, gathering matter into webs while leaving most of space almost bare. When cosmologists reconstruct the three-dimensional velocity field of our region, Laniakea appears as a bright, sloping ridge on the wall of a depression, the KBC void. The supercluster is not a fixed continent, but a current of galaxies, pulled by some basins of attraction and released by the hollows behind. The more precisely we map this, the more the cosmic web looks like a living flow rather than a static scaffold. Matter circulates. Voids grow. Filaments stretch and drift. That naturally leads to a deeper, quieter question. If one supercluster, like Laniakea, can float inside a void, could there be larger hollows, still immense, unseen valleys shaping the flows of galaxies? The pattern of background radiation, even the way we read the light from the Big Bang. To look for those, astronomers turn to one of the most delicate tools in their kit, the fossil sound waves left over from the early universe. About 400,000 years after the Big Bang, the universe was not yet filled with stars. It was a hot, dense plasma of protons, electrons, and photons all tangled together. In that fluid, gravity tried to pull matter into clumps, while radiation pressure pushed back, creating waves of compression and rarefaction, true sound waves, pulsing through the young cosmos. Today we call their imprint baryon acoustic oscillations, or BAO. The sound itself has long since faded, but the pattern it left remains frozen in the large-scale distribution of galaxies. Each wave carved out a preferred separation between clumps of matter. On cosmic maps, that shows up as a very faint tendency for galaxies to be spaced at a characteristic scale, roughly a few 100 million light-years apart. That scale acts like a standard ruler. By seeing how stretched it is at different distances, we can tell how much the universe has expanded over time. When researchers apply this ruler to our own part of the cosmos, they find something subtle but telling: the BAO scale. Here, the frozen echo of those ancient sound waves looks slightly larger than it does in models of a perfectly average universe. It is as if the ripples were pulled just a bit farther apart. The simplest explanation is that space in our neighborhood has expanded a little more than the global norm. In other words, the BAO pattern itself whispers that we live inside a bubble of faster expansion. Large surveys like the Sloan Digital Sky Survey, DESI, and others map millions of galaxies in 3 dimensions to tease out this pattern. When they compare the observed BAO signal around us to what you'd expect in a homogeneous universe, the mismatch lines up neatly with the idea of a broad underdensity, a void of about the size and depth of the KBC region. The galaxies are not wrong. It's the space between them that has been stretched. In that sense, the BAO measurement becomes a kind of seismograph for the early universe. Each wiggle in the graph is a fossil sound wave, a pressure ripple that once rang through the primordial plasma. Where those ripples look evenly spaced, expansion has followed the average script. Where they are a little too wide, as in our area, it hints that the local fabric has been pulled extra taut. This doesn't just support the existence of a void, it also feeds back into our estimates of cosmic expansion and age. If the standard ruler is slightly stretched here, then any Hubble constant we infer from local distances will reflect that stretch. Our piece of the cosmic symphony is playing in a slightly faster tempo than the orchestra as a whole. Astronomers sometimes describe BAO as the heartbeat of the universe, a rhythm frozen into the geometry of everything. When we listen closely and hear that rhythm sounding a bit off in our neighborhood, it's not necessarily a sign that the heart is sick. It may simply mean that we are standing at a spot where the echo has been warped by a long, slow wave of emptiness. As future data from Euclid, DESI, Webb, and other instruments refine these measurements, we'll know more precisely how stretched those ancient ripples are in our corner of space. If the BAO pattern continues to point to a significant local underdensity, then the KBC void stops being just an interesting idea and becomes a fundamental part of the cosmic map, a structural feature that must be accounted for in every distance, every redshift, every timeline we extract from the sky. It's a quiet thought that the universe's first sound waves are still speaking to us, telling us that we live in a rarefied valley, a slightly overstretched patch of space-time. We simply had to learn how to read the pattern of their frozen rings. And once you realize that, another question rises like a faint glow before dawn. If the void leaves its mark on the way galaxies are spaced, could it also have left a trace on the oldest light itself, the soft afterglow of the Big Bang that still bathes the universe in microwave radiation? If the first ripples of sound in the young universe can tell us that our corner of space is stretched and thin, it's natural to ask whether the oldest light itself carries the same story. The cosmic microwave background, the CMB, is that light. It comes from a time when the universe was only about 380,000 years old, when electrons and protons finally paired up into atoms and the fog of charged particles cleared. What had been trapped, light was suddenly free to travel, and it has been crossing the universe ever since, cooling and reddening as space expands. Today it arrives as a bath of very faint, very uniform microwave radiation, the closest thing we have to a baby picture of the cosmos. But the universe did not stay smooth. Over billions of years, matter clumped into galaxies and clusters, and vast voids opened between them. When CMB photons thread their way through this later structure, they don't pass entirely untouched. They gain and lose tiny amounts of energy as they fall into and climb out of gravitational wells, and as they cross regions where the expansion itself is accelerating. Those minute changes leave their mark as subtle hot and cold freckles on the microwave sky. One particular freckle has haunted cosmologists for years: the CMB, cold spot, a patch of sky unusually large and unusually cool compared to the gentle modeling around it. It was first clearly seen in maps from WMAP and later confirmed by Planck. On the sky, it spans several degrees, and its temperature is tens of microkelvin lower than the surrounding average. A tiny difference, but far larger than simple random noise would suggest. For a long time, no one was sure what to make of it. Then, when astronomers overlaid these temperature maps with three-dimensional galaxy surveys, a remarkable pattern appeared. Behind the cold spot lies a huge underdensity, a supervoid in the direction of Eridanus, hundreds of millions of light-years across. The alignment is hard to ignore. It looks very much as though photons from the early universe cooled a little extra as they crossed that hollow. The mechanism behind this is called the integrated Sachs-Wolf effect. Imagine a photon from the CMB entering a void. As it falls into the region's shallow gravitational potential, it gains a bit of energy. But because the void is expanding and its gravitational well is slowly changing as dark energy pushes space apart, the photon doesn't quite give up the same amount of energy when it climbs back out. It emerges with a tiny deficit, a little cooler than when it went in. Do this for unimaginable numbers of photons across billions of years, and you get a faint, cold patch on the sky. The reverse happens in very dense regions. Photons come out slightly warmer. The shifts are tiny millionths of a degree, but satellites like Planck can measure temperature differences that small. When researchers stack CMB data around many known voids and compare it with random regions of sky, they find a consistent pattern. Light that has passed through underdense regions is, on average, just a bit cooler. The universe's emptiest places act like very soft, very large coolers for its oldest light. That means our voids aren't invisible. Even if we can't see them directly with our eyes, they leave fingerprints on the CMB. Analyses of the sky suggest that not only the Eridanus supervoid, but other large hollows, including parts of the region we call the KBC void, may be responsible for some of the subtle cold features in the microwave map. If that is true, then the photons bathing our telescopes have carried the story of our own emptiness with them for almost the whole age of the universe. The CMB, then, is more than a snapshot of the past. It is also a record of the journey. Its light has been stretched by expansion, nudged by gravity, cooled by voids, and warmed by clusters. Modern instruments read these tiny temperature and polarization patterns like grooves on a cosmic record, inferring where space-time is deep, where it is flat, and where it is growing fastest. The wrinkles in the CMB are not random. They are a map of structure and a tracer of dark energy's influence. Once you realize voids can write on this ancient canvas, another thought follows. If our void and the Eridanus supervoid are large enough to leave marks, are they rare exceptions or just the most obvious members of a much larger family? As galaxy surveys have improved, the answer has become clearer and stranger. It turns out that the universe is riddled with these hollows. Between the glowing filaments and clusters, there stretches a network of supervoids, enormous patches where the density of matter falls far below the cosmic average. Our KBC void is one, the Eridanus supervoid is another, and as astronomers map fainter galaxies and push deeper into space, they keep finding more. In the simplest cosmological models, truly huge voids, hundreds of millions of light-years wide, with substantial underdensity, are supposed to be rare. They form from slightly underdense regions in the early universe that expand a bit more quickly than their surroundings. Simulations suggest that a few such giants might appear by chance, but the more we look, the more candidates we see. Extended low-density zones that, taken together, seem to occupy most of the universe's volume. That realization flips our intuition. The cosmos is not a mist of galaxies with occasional gaps. It is mostly gap, with matter strung out along its edges. On the largest scales, the universe looks less like a uniform fog and more like foam. Bubbles upon bubbles, with galaxies, groups, and clusters as the thin, bright seams between them. Each of these great hollows can, in principle, leave its own faint signature on the CMB, just a slight cooling, a small distortion in the pattern of temperature and polarization. Some may overlap along our line of sight, blending into complexes of underdensity that stretch across billions of light-years. When cosmologists compare CMB anomalies with the layout of these voids, hints of such complexes appear, chains of emptiness that seem to line up with cold features in the microwave sky. For our theories, this is both a challenge and an opportunity. If supervoids as large and deep as the KBC and Eridanus regions are common, they push the standard lambda CDM model, our baseline picture of dark matter, dark energy, and general relativity, to its statistical limits. Perhaps the early density fluctuations were a bit larger in some modes than we thought. Perhaps dark energy or gravity behave differently in low-density environments, allowing voids to grow more than expected. Or perhaps our models are broadly right, and the universe simply drew a surprisingly extreme hand in a cosmic lottery. Either way, these hollows are no longer a footnote. They shape how we measure distances, how we infer the expansion rate, how we interpret the CMB. Living inside one means that every ray of ancient light we see has been gently bent by the underdensity beneath our feet. Our view from here is tinted by the geometry of emptiness. Future missions and surveys mapping gravitational lensing, tracing galaxy flows, refining CMB temperature and polarization maps will help us pin down exactly how many supervoids there are, how big they can be, and how strongly they interact with light and expansion. If their numbers and sizes line up neatly with our models, we'll have yet another confirmation that simple physics can give rise to such a delicate architecture. If not, they may be pointing us toward new physics, hiding in the quietest corners of space. For now, when you look at an image of deep sky, a cluster glowing softly, arcs of lensed galaxies curling through the frame, it's worth remembering that the blackness between those lights is not just nothing, it is structure, it is context. It is the scaffolding that lets the bright parts make sense. If the KBC and Eridanus voids are only the first giants we've recognized, then perhaps the most haunting question left to us is not about what the universe contains, but about what it deliberately leaves fallow. The cosmic web is drawn as much by absence as by presence. In the end, the shape of everything may be set not only by what fills the universe, but by what leaves it empty. If the universe really is laced with great hollows, and if our own home lies inside one of them, then a quieter, more unsettling thought starts to form. What if the way we see the expansion of the cosmos has been gently tilted by the bubble we live in? For about a century, cosmologists have described that expansion with a single number, the Hubble constant. It tells us how fast distant galaxies recede from us for each unit of distance. When we measure it nearby, using supernovae and variable stars in galaxies out to a few 100 million light-years, we get a value around 70-something kilometers per second per megaparsec. When we infer it from the cosmic microwave background light from when the universe was a baby using instruments like Planck, we get a lower value in the high 60s. That mismatch, the Hubble tension, has refused to disappear. Each side has refined its methods, trimmed its uncertainties, and the gap has only grown sharper. It's as if the early universe and the nearby universe are whispering different speeds. One way to make sense of that is to imagine that our neighborhood is not typical if, as several lines of evidence suggest, the Milky Way and its surrounding galaxies live inside a broad, underdense region, roughly a couple of billion light-years across. Then space here would be expanding a little more freely than average. With less matter around to pull back, gravity's slowing effect is weaker. The fabric of space in our patch can stretch a bit faster. Astronomers sometimes call this idea a Hubble bubble, a region where the locally measured expansion rate is elevated compared to the global one. It doesn't mean the laws of physics are broken just beyond its edge. It simply reflects how general relativity works in a lumpy universe. In Einstein's picture, regions with less mass experience less deceleration. Over cosmic time, even modest underdensities can translate into noticeably faster local expansion. When observers line up distances and redshifts for many nearby supernovae, they do see a pattern that fits this story. Within a certain range, galaxies appear to be receding, slightly faster than you'd expect if our region had the cosmic average density. And as they push to larger scales, beyond the inferred edge of the void, the behavior drifts back toward the slower rate suggested by the microwave background. If that is truly what's happening, then both sides of the Hubble tension could be telling the truth. The early universe measurements reflect the average behavior of the cosmos as a whole, while the local ones capture the expansion inside a particular hollow, our hollow. The universe isn't playing a trick on our instruments. It is only reminding us that perspective matters. We are measuring its growth from inside a patch of space-time that is, in a quiet, statistical way, special. The consequences are subtle but far-reaching. A faster apparent expansion here would, if taken at face value, make the universe seem a bit younger than it really is. Timelines for the formation of galaxies, the growth of structure, even the evolution of dark energy could all carry a slight bias if they are based solely on our local view. And if other large voids host their own observers, they too might read off slightly different values, their own local tempos in the broader symphony. Future missions and surveys will help us test how far this bubble effect goes, whether the expansion rate truly relaxes beyond our underdensity, or whether the differences persist on still larger scales. But even now, one conclusion feels safe to hold gently in mind. Our region of space is not perfectly average. We live in a slightly overstretched pocket, a calm bay in an uneven cosmic tide. Every number we write down bears the faint thumbprint of that setting. Once you've seen that, it's hard not to wonder what else the void changes. If it can nudge the flow of galaxies and our reading of the universe's age, what does it do to the galaxies that drift through it? What kind of life, cosmic life, unfolds in such a quiet place? Out near the edges of clusters, where gravity runs wild, galaxies crash together and tear each other apart. Gas is stripped, stars are flung, black holes feed and flare. The dense nodes of the cosmic web are places of constant interruption, but inside the voids, in the wide, dim hollows between those knots, the story is different. Voids make up the vast majority of the universe's volume. They don't look like much in images, mostly darkness with a few scattered smudges, but those smudges are galaxies too, living in some of the gentlest conditions nature can provide. Astronomers simply call them void galaxies. Surveys that catalog them show a pattern. On average, void galaxies are smaller and lighter than their cousins in crowded regions. They are often bluer, meaning they are actively forming stars, and they tend to be rich in cold gas that has never been stripped away by ram pressure or stolen in a close flyby. They have lived comparatively quiet lives. With few neighbors and weak tidal forces, their disks remain intact, unwarped by repeated encounters. Infrared and ultraviolet observations suggest that many of these galaxies are still forming stars today, more than 13 billion years after the Big Bang, at a slow but steady pace. In clusters, star formation often comes in bursts, triggered by collisions and then quenched when gas is blown out or heated. In the voids, it looks more like a long, low fire, less dramatic, but more persistent. Simulations back this up. When cosmologists model structure formation in a realistic cosmic web, they see halos of dark matter forming more slowly and at lower masses inside underdense regions. Gas falls into those halos, but with weaker gravity and fewer shocks, it cools gently. Star formation starts later and proceeds more gradually. There are fewer major mergers to scramble or truncate that process. Over time, this leaves a population of galaxies that in some ways resemble the universe's youth, metal-poor, gas-rich, and relatively undisturbed. Observers sometimes describe these systems as living fossils. By studying them, we get a window into how galaxies evolve when the universe leaves them mostly alone. Their chemistry, their star-forming regions, their quiet disks all carry information about what happens when you remove the constant harassment of a cluster environment and let gravity and cooling gas do their work in slow motion. And in the back of many minds, one more question lingers softly. What would it mean for planets and potential life to grow up in such places? Fewer nearby supernovae would mean fewer intense blasts of radiation. Fewer close encounters with other galaxies would mean more stable orbits for stars and their planets. Even the slightly cooler background and lower rate of disturbances might, over long stretches of time, offer a different kind of cosmic shelter. It's far too early to say whether void galaxies are especially good cradles for life. Those are questions for future instruments and future generations. But the thought fits with a deeper pattern the universe seems to hold, that extremes of chaos are balanced by pockets of calm, and that both are necessary for the full story. The voids are not failures. They are not regions where the universe forgot to make anything. They are part of its breathing. By expanding faster, they help regulate how matter flows, how filaments stretch, how clusters grow. By being quiet inside, They give some galaxies the chance to follow a different rhythm, less hurried, less violent, more enduring. When you look at a map of the cosmic web, with bright strands of galaxies wrapping around vast, dark cells, it's tempting to focus only on the light. But in many ways, the hollows are just as important. They are the spaces where expansion runs ahead, where ancient light cools, where galaxies evolve in slow, steady arcs. In that sense, emptiness is not the absence of creation. It's the condition that lets creation breathe. If emptiness can slow the growth of galaxies and tilt our measurements of the cosmos, it's natural for the mind to drift one step further into a quieter, more distant future and ask, what happens when the thing pushing everything apart finally wins? Today, the universe still feels full. Galaxies cluster, stars burn, gas glows. Gravity has built an intricate web and holds many of its threads tight, but on the very largest scales, another influence already dominates. We give it a simple name, dark energy, but what we really mean is that space itself seems to carry a kind of pressure, one that urges it to expand faster and faster over time. For a long while after the Big Bang, matter and radiation were in charge. Their gravity slowed the expansion, tugging against the initial outward rush. Then, a few billion years ago, the balance tipped. As the universe thinned and matter spread out, this strange, uniform energy in the fabric of space began to outweigh everything else. Observations of distant supernovae in the cosmic microwave background suggest that this transition happened roughly 5 billion years ago. Since then, the expansion has been accelerating. On human scales, that acceleration is nothing you can feel. Our galaxy is bound to itself. Our local group is anchored by gravity. But beyond those local islands, space is already stretching fast enough that some galaxies are receding from us faster than light. Not by moving through space that quickly, but because the space between us and them is growing that quickly. Their light, once it has gone too far, will never reach us. This gives the universe a kind of horizon, a soft boundary in time and distance, beyond which events are, in a very real sense, removed from our possible experience. As dark energy continues to push, that horizon will close in. In roughly 100 billion years or so, if our best models are right, every galaxy beyond our small group Andromeda, Triangulum, the faint dwarfs that share our filament, will have slipped beyond visibility. The night sky will belong almost entirely to a single merged system, sometimes nicknamed Milkdromeda, a fat, quiet ellipsoid of old stars circling a swollen black hole at its heart. Outside that island, there will still be a universe. Clusters will still exist, stretched across expanding voids. But no light from them will ever arrive here. For any observers living in that far future, the cosmic web will be an invisible rumor. There will be no way to know, from direct observation, that the universe was once crowded with other galaxies. The fading will continue. The faint glow of the cosmic microwave background, the afterlight of the Big Bang, will be stretched to such long wavelengths that it slips beneath any practical detectability. What we now see as a gentle radio haze will be drawn out into unimaginably long, cold waves. To eyes and instruments in that deep future, the universe will no longer have a visible beginning. Space will look static, empty, and timeless, even though it is still expanding. Meanwhile, within each isolated island, another kind of story unfolds. Stars are not infinite. Gas reservoirs are not infinite. Over about 10 trillion to 100 trillion years, the raw material for star formation will be used up or ejected. The bright, short-lived suns will all have burned, leaving only long-lived, dim red dwarfs to carry the light. Eventually, even those will exhaust their fuel and fade. What remains is sometimes called the degenerate era. The universe becomes a scatter of remnants, white dwarfs slowly cooling toward blackness, neutron stars spinning down, black holes silently anchoring the ghostly cores of dead galaxies. Gravity still acts, but the sources of fresh, bright structure are gone. New stars are rare or non-existent. The universe does not end in a flame. It drifts toward embers. Even the embers will not last forever. According to our best understanding of quantum fields near horizons, black holes should leak over unthinkable spans 10 to the power of 60, 10 to the power of 80, 10 to the power of 100 years. Depending on their mass, these holes evaporate, bleeding their mass away in a faint drizzle of radiation. The largest, the giants at galactic centers, will be the last to go. In their final whisper, the last concentrated knots of gravity will unspool back into diffuse particles and light. What's left after that is a state poets and physicists both find hard to describe. A universe that is still expanding, but almost perfectly empty. Energy smeared thinly and evenly, with no clumps to collapse, no gradients to drive change. A near absolute quiet. In thermodynamic terms, it's called heat death. Not because everything is hot, but because all the useful differences, the contrasts that allow structure, motion, and life, have been spent. This is the future we forecast if dark energy behaves as a true cosmological constant, a steady property of space that never changes. Current measurements of its equation of state, the way its pressure relates to its density, are all consistent with that simple picture. Within our errors, it looks constant in time and uniform in space. In that case, the universe's fate is one of slow thinning and growing solitude, not sudden catastrophe. There is a more dramatic possibility tucked into the equations, though. If dark energy's pressure is even more negative than a pure cosmological constant, if its equation of state parameter dips below -1, then the acceleration becomes more than exponential. The scale factor of the universe races upward so quickly that, in a scenario sometimes called the Big Rip, even structures that are currently safe would eventually be torn apart. First clusters, then galaxies, then stars, then planets, and finally, the atoms themselves would be pulled asunder by the runaway expansion. So far, the data don't favor that path. The numbers cling close to the quiet line of a constant dark energy, but we are still learning, still tightening our constraints. Telescopes that map how galaxies cluster over time and how supernovae trace the expansion help us check whether dark energy has been truly steady or whether it has drifted slightly across cosmic epochs. For now, the calmer fate seems more likely. A universe that keeps doing what it is already doing, just more so. Islands of matter drifting apart, each wrapped in its own cocoon of darkness, each eventually becoming a little private cosmos of fading stars and quiet remnants. Expansion wins, not by tearing things apart in a flash, but by letting everything run down in its own time, until there are no more gradients left to exploit. If you lean into that picture, there is something both chilling and strangely tender about it. On the one hand, it means that isolation is not a temporary inconvenience. Given enough time, it is the natural end state of everything. Every cluster secluded, every galaxy marooned, every last spark of light decoupled from all the others. On the other hand, it also suggests that the era we live in now the time of bright stars, complex chemistry, and large-scale structure is something precious and brief. We live in a window when the universe is both old enough to have become interesting and young enough to still show us its wider pattern. And there's another layer to the loneliness that dark energy writes into the future. It doesn't only separate galaxies, it also walls off perspectives. If the cosmic web is filled with voids like ours, each containing thousands of galaxies, then there is room for many other islands to host their own observers. Each of those observers would look out across their sky and, using their own version of the distance ladder, measure how fast space seems to be expanding. If they happen to live in an underdense region, as we do, they would see a slightly elevated local expansion rate. If they live in a denser filament, the opposite might be true. Each vantage point carries its own bias. For civilizations in distant pockets, the story of isolation would unfold in ways eerily similar to our own. They would watch more and more galaxies slip beyond detection. They would one day lose the cosmic microwave background in the noise. They would be left with only a small, bound collection of stars overhead and no direct sign that they are part of a much larger web. In that sense, every technologically advanced species may, if it survives long enough, eventually become cosmologically blind, not through lack of curiosity, but through the limits imposed by accelerating space. The information they would need, the early universe light, the shared structures in the distance, will simply no longer be reachable. Today, we are not yet in that position. Our horizon still stretches far. We can still see filaments, clusters, and the afterglow of the Big Bang. We can still map voids and test whether our patch is unusual. We can, for a little while longer, place ourselves in context. If there are others out there, scattered through other voids and along other strands, their instruments may be doing the same work, tuning to faint microwaves, plotting galaxy catalogs, trying to decide whether their local value of the Hubble constant is truly universal. They may be running into their own tensions, their own puzzles, where nearby and distant measurements disagree, and wondering if they, too, live inside a bubble. We may never exchange signals with them. The accelerating expansion makes that almost certain on large scales, but there is a different kind of connection in knowing that any mind that looks outward with enough patience will face similar questions. Every observer who measures the sky is, in a way, tracing the same laws from a different angle. Dark energy, then, is not just the force that will thin the universe. It is also the thing that guarantees that no one vantage point is complete. It limits what can be shared, but it also links all perspectives through a common mathematics. The expansion that will someday leave each island alone is the same expansion that once drew matter together into webs and lit the first stars. We live in the middle of that story. The void around us is still forming. The distant galaxies are still visible. The microwave background is still there, humming softly. The same physics that points toward a distant quiet also gives us, right now, a universe rich enough to study, to model, to turn into a kind of lullaby about where we are and where everything is going. And for the moment, before that future solitude arrives, there is still something deeply human in simply noticing it, that we, in our small corner of a thinly filled bubble, can trace the outlines of a fate shared across all of space, a long, slow drift into darkness, and the brief, bright interval in which the universe knows itself through the eyes that have opened inside it.